Yeah, so everybody, welcome to the Spring 2022 UTIG Friday seminar series. Kicking off today with a talk on an exciting new technique for looking at near-surface geophysics, distributed acoustic sensing. And it will be brought to us today by Ariel Lellouch, who is an assistant professor at the Tel Aviv University. Ariel got his BSc at Hebrew University in Jerusalem, spent a few years in industry, and then came back to do graduate work at Tel Aviv University, and is now positioned there via a postdoc at Stanford. Looking forward to his talk today. He does have some slots free after noon Central Time to speak to him. So Constantino will put the link in the chat if you wish to sign up for that. He has been talking to some people this morning already. So with that, take it away, Ariel.
Cool, thanks. I mean, honestly, I spent a few years in the army, not the industry, but I guess it kind of counts as some sort of practical experience. So anyway, yeah, thanks for the introduction. And for stepping in and making sure this seminar runs smoothly. Quite happy to be with you today, at least on the temporal axis. Even though you can see in my background, it's already night here. Really wanted to visit in person while I was in California, but there was this small virus situation. But anyway, I guess it's the next best thing. And well, speaking of California, I'd say this talk is more or less a summary of what I did during my postdoc with the Stanford Exploration Project. I'd say, like, in terms of kind of an umbrella term, we're going to be talking about seismic applications, so the seismic band, let's say between 3 and 800 hertz. We're going to go as high as that, but we're going to do that with fiber, and more specifically downhole fiber. You can probably guess from this very long list of collaborators that this is going to be a relatively kind of broad talk. I should say I'm not claiming this is a complete representation of the topic at hand. It's just the things that I worked on. And hopefully it will give you some notion of what could maybe be done with downhole fiber. So we'll start with why distributed acoustic sensing, DAS, fiber sensing, in general, and more specifically, why the downhole environment. And then the two main portions of the talk, they're quite applicative. We'll start with seismic monitoring with vertical arrays. I'll describe, I think, a pretty cool and easy to implement detection workflow, how we applied it to both seismic and microseismic activity in the geothermal project, and a little bit of more advanced analysis, event location, and magnitude estimation. Second part, we're going to go into horizontal fiber, deep into an unconventional reservoir, in which we have a deviated well targeting that reservoir, instrumented with a fiber. And we'll talk specifically about guided waves. It turns out that this reservoir is actually a waveguide for seismic waves. We'll describe their propagation properties and how we use them to estimate horizontal fracture growth using perforation shots, and also do some more traditional microseismic analysis. And hopefully from all of this, try to draw some conclusions. So I suppose this is redundant for at least some of you, but just really the basic principles of DAS, or fiber optic sensing. The idea is we have an optical cable, and we've got our box attached to one of its ends. And this box continuously sends pulses of light in the form of laser through the fiber. Now, the idea is that when the fiber is at rest, you're going to see a constant pattern of backscattered or reflected light. Optical fibers are close to ideal, right? That's why internet can go from Tel Aviv to you, but they're not completely ideal. So there's always a small portion of the light that is actually reflected back to the box. Now, this pattern is constant as long as the fiber is at rest. When things get interesting, for example, when you've got a seismic wave impinging on the fiber, this is going to distort the fiber a little bit and create a change in the pattern of the reflected light. And it turns out that the phase change of the light, this is basically a big interferometer, is quasi-linear to the elongation or compression, more commonly known as strain, along the fiber. Now, the thing is, if you think about a photon, for example, reflected from this point, it's going to be accumulating strain along the entire path. So that's not something that is extremely useful. However, we do know the speed of light in the fiber. So if we can send these pulses of light with some special encoding, when we get some light back, we can kind of detect its special signature, how much time has elapsed, therefore how much distance that specific packet of light has traveled, and then we can actually break down the profile of strain as a function of distance along the fiber. And if we do this type of analysis fast enough, we can get the strain as a function of location along the fiber and time. And that's the distributed nature of the measurement. And if we're looking at kind of like the latest and greatest technology, we can get to pretty high resolutions. I mean, we're talking about roughly, let's say, 1 meter spacing between measurement points, about 1,000 samples per second, and about 40,000 channels. So we can get, again, with the latest and greatest, we can get 40 kilometers of fiber sampled all at once in very high spatial and temporal resolution. And this is, I think, really important as a downhole sensor. But there are also some, let's say, some logistical or some practical advantages for which DAS is, I think, extremely useful for that. The first is that you can use DAS in an active well, simply by putting the fiber outside the casing, as you can see in this image here. Traditionally, if you want to do seismic monitoring in a borehole environment, you had to drill a special well where you could put your instruments. With fiber, you can just piggyback on existing wells. Also, the fiber is very resistant to temperature and pressure, much more than traditional electronics based. Therefore, you do have to pay some one-time installation cost, but you can get closer to the target reservoir. Plus, once the fiber is installed, it stays there for a very long time. I'm not going to show data in this talk, but I worked on some data acquired at Seifod in 2017, and the fiber was installed in 2005. So 12 years later, when DAS was not even a consideration, you can just go back to that fiber and acquire data. So that if you're into 4D or time-lapse studies, this is extremely useful. DAS as a tool, because of the way the optics work, has an extremely wide frequency range. I'm counting at least 8 orders of magnitude. On the very slow end, you can go to scales of hours. People have been looking at strain change, pressure fronts, frac hits, things like that. You can go all the way up to listening to leaks, listening to acoustic emissions in fluid flow. As I mentioned, we're in the seismic range, so somewhere in the middle, but DAS offers quite a lot of measurements, all in one package. And eventually, that's what I'm trying to advocate for, is that we get such a high resolution measurement of the seismic wave field that we have to think in terms of array processing. And I'm sure you are all very familiar with such approaches from the nature of your work. So let's get down to the first example. That's a seismic monitoring project, FORGE. It's a DOE-funded project for geothermal energy, located in Utah, in an area known as the Renewable Energy Corridor. And this is the site. So we've got 2 wells. Let's start with the map view. We've got 2 wells, a stimulation well and a monitoring well. In this case, they are separate because the monitoring well also has traditional sensors. So that actually shows you why DAS is important, because you could save that monitoring well. But anyway, that's what they did. And we have also these traditional seismological stations in blue triangles maintained by the University of Utah. So we've got these 2 wells. The magenta one is the stimulation well. The orange is the monitoring. You can see they both cross this gray surface, which is some granite contact. But what's interesting is these 2 surfaces. They are, of course, approximated, but these represent surfaces of equal temperature. So you can see this is 175 Celsius and this is 225 Celsius, meaning the stimulation well actually gets to a temperature of close to 200 degrees. And that's where actually the geothermal experiment is supposed to take place. So again, maybe redundant for some of you, why do we even need seismic monitoring in such a case? If you think about the geothermal project, you need 3 things, right? You need heat, you need some fluid that can draw that heat from the earth, and permeability, basically a way for that fluid to flow and have surface contact from which it can draw the heat. In EGS, or enhanced geothermal systems like this one, you have hot rock, but you don't have a fluid. You can just think of a hot block of granite. So drawing from the hydrocarbon industry, we're basically going to do some hydraulic stimulation by high pressure injection and trying to open or activate existing fracture networks. This way you can create the permeability, and eventually we're going to inject the fluid, draw some heat, and then extract it and convert it to energy. And when you do that, you need seismic monitoring. You need to monitor microseismic events because you want to understand the way your fracture networks grow. That's critical to the success of the project. But you also need seismic monitoring in the higher range of magnitudes because you have a threat of induced seismicity. And there have been many examples of geothermal projects in Korea and Switzerland that have been stopped simply because the fluid injection basically changed the stress regime and caused some induced earth. That's why seismic monitoring is important here. So let's look at let's start with earthquakes, kind of the induced seismicity maybe risk. Let's see what earthquakes usually look like. So we're going to start with the traditional network, as I mentioned, the blue triangle. So I put some 6 time windows. And if we look at the top, and we have 7 stations, each one has 3 components like Z, so vertical, east and north. So if you look at the top row, you can see events that are relatively clear. You can pick the P wave, the S wave. Middle row, it starts being a bit tricky if you're a good seismologist, and I did not pick those, a real seismologist picked those. You can probably still pick things, and in the bottom, it looks like, well, like noise. If we look at DAS, I think things are easier to understand. So just so we get used to these plots, so this is the depth, so it goes from 0 to about 1 kilometer down. This is time. The strong events that were visible on the surface, we can see, I think, a wavefield that we recalled over the DAS. So we can see this phase here. It gets to the bottom of the earth first, quite weak. We can follow it as it goes up, as it gets to the surface. We can see along the way, it also has some downgoing reflections. These are probably linked to some aquifers. So basically, as they cross, as these waves cross the geology, they reflect down. Later, we can start seeing the shear wave. We see some S2P conversion, of course, some free surface reflections. But the point is, I think if you're not a seismologist, this is a lot easier to understand than this. Also, on the more, let's say, again, practical side, if you're looking at the weakest events that on the surface were completely invisible, here you can actually see them, right? You can see the P wave, you can see the S wave, P wave, and maybe slightly weak S wave, but it looks like there is potential for kind of doing better than the surface array for event detection. So how do we do that? Trying to go for a simple approach. The first thing we have to kind of assume, and it's not our choice, it's kind of the limitations of that we have a measurement of strain, but it's strain along the direction of the fiber. So that means we have a unidirectional measurement, and as a result, we have complete azimuthal symmetry. That's a problem, but once we kind of live with this assumption, we can assume that the events are quite far from us, and therefore they reach the array as a plane wave. And we can also assume that they get to the bottom of the array first, because we're interested in deep earthquakes. And in the ideal case, which is the easiest probably in terms of geophysics, you would have the source far below and directly below you. So in this case, we can assume the propagation is going to be 1D. It's going to be straight through the array. And then if you look at 2 adjacent DAS channels, the time difference is going to be the depth difference divided by the velocity, right? That's like the easiest exercise in geophysics, like a reverse VSP 101. Now, of course, we don't control the earthquake, so they might be coming at an angle. But if it happens, it's only a scaling of the cosine theta factor. For those of you who remember, it's like an apparent velocity from a dipping layer in the NMO equation. So we're going to use that to say something about the velocity first. The problem, of course, is we need a good subsurface source. So if we have an earthquake, it's useful, but we have something better, right? We have a perforation shot. Before stimulating, and in this case, the experiment never got to the injection phase, but they did get to the stimulation phase. So there were perforation shots. So that's basically a controlled detonation for which we know the exact location. So we can look at the data from these perforations. This is what they look like. We can basically follow the P wave, either manually, automatically picking it, or even some slant stack or radon decomposition, which is what we did here. You can basically estimate the slopes here and the slope of these arrivals after you correct for the angle of arrival, which is easy to do because everything until the bottom of the array is in granite. You can basically build the P-wave velocity along your array. You might have noticed that there are no shear waves, and that's because the perforation shot is an explosive. So instead, we chose a microseismic event, estimated its location from the P-wave, and then used the S-wave velocity here to build a velocity model. This is all technical and maybe not super interesting. The important thing is the bottom line. If you look at the velocity models we derived for shear and P-wave velocity, the continuous lines are from the DAS data, and the dashed ones are from sonic log. So we are basically able to estimate the velocity profile along the entire DAS portion, which we did not have. You can see that part was not logged. So that was just the velocity model building. So we went from travel times to subsurface velocity. For detection, we're going to go the other way around. We're going to assume we know the subsurface velocity, and we're going to predict what the arrival times should be as a function of the event location. And more specifically, it only depends on the angle of incidence that the plane waves get to the array at. So we're eventually looking at a single parameter scan, which is simply the angle of incidence at the bottom of the array. Of course, because the velocity within the array changes, you also need to iteratively take into account the fact that the plane wave change direction along the array, but it's still a single parameter scan once you know the velocity model. So what we're going to do is basically look at our data, predict the travel incidence, apply some time shift to the data based on this prediction. And if we got it right, things should be flat. Things should be coherent after we apply this time shift. This method is good because it's peaking free. And when you're looking at continuous DAS data, peaking can be a pain. We're talking about a lot of data and quite noisy on the individual channel level. And as a byproduct, we're going to get the angle of incidence at the bottom of the array. So just to show you what it looks like in practice, I'm going to show you some P-wave arrival from one of the microseismic events, I think. And I'm going to show you basically time shifts for different angles of incidence. So angle 0 is assuming the event is directly below us. I'm going to start this as a movie. For the first angles, you're not going to see much change. But as the angles start growing up, you will see that this phase, this P-wave phase, is going to get more and more flat. So more and more coherent, meaning we got the angle right. And this is just a semblance measure. You can use any other that you want, but basically it seems like at around 60 degrees or something like that. Let me see if I can catch it. Well, never. At around 60 degrees or something like that, we get the highest semblance. So that means that's the angle of incidence. And from a detection perspective, you just need some thresholding method, and you can use this semblance or any other coherency measure to detect events. So that's how we did it. We applied it to about 10 days of continuous DAS data. And during that time frame, we had 4 events in the standard kind of like mass production analysis of the traditional seismic network. And with DAS, we could find 82 events. We tried to link them to activities in the well, but the total injected volume was so low that there was no link. But the important thing is that we could see a lot more with the downhole DAS compared to the surface array. And it's not super surprising, taking into account what I showed earlier, I think, that you could see weak events that were invisible on the surface. And we even tried to go back to the surface array, knowing when to look for things. And we could still see only about 20% of the events. And if you do some like very basic magnitude completeness calculation, it looks like downhole DAS is better by, let's say, an order of magnitude, maybe half an order of magnitude, but still a pretty subsequent advantage compared to the surface array. You can also pick some interesting events, and I'll go back to this at the end of the talk. I like to kind of, it's not really a riddle, but what do you think this event is? So yeah, maybe let's take a few seconds, and then towards the end of the talk, I'll reveal what I think this is. No prizes for correct guesses, I guess, but maybe some small challenge. We're also able to use the same experiment for microseismic monitoring. And for that period of time, there were downhole traditional geophones in the monitoring well, the bottom third, and everything was deployed and processed by Schlumberger, so kind of like cutting edge, industry-grade processing. And one of the cool things is that we had recording at the same time. So we can look at the microseismic event, both on and at downhole geophones at the same time. That's something that's not often available to us. So I'm plotting the z-axis of the downhole sensor, of course. You can see 12 tools. One of them was dead, so I didn't plot it. And you can see DAS in the background. So you can see, I think, you get what each type of sensor gives you. So the geophones are very quiet and great signal to noise ratio. And for the P wave, it's easy to understand what happens. But when you're getting into the more complicated phases like the S phase, and then what appears to be an S2P at the granite contact, you have to be a really good seismologist to understand all of that just from the green traces. Whereas when you have DAS, I think that the spatial coherency really helps you understand what's happening, and you can really differentiate between the different phases. Another cool thing, by the way, here is you can see the effect of the surface noise, right? So this has an inverse move out, means it starts at the top and then goes down. So we know it's noise. And you can actually see that below about 100 meters, you get to a quiet level. And that could explain, by the way, why the surface array was really underperforming compared to DAS, because most of the DAS is in this like sub 100 meter area or sub 150, in which things are very, very quiet. You can also see, by the way, this reflection here that we mentioned earlier. So I think that's kind of like, I don't know, best of both worlds, or some way to look at it like that. In terms of detection, DAS, so I ran exactly the same algorithm that I mentioned before. DAS did not do as well as downhole geophones. Of course, we have to say we're comparing like my own algorithm compared to Schlumberger and all their years of experience and expertise. So maybe it's not a fair comparison, but even with like a first attempt, I could find, I think it was about 120 events with DAS compared to 300 with the microseismic. And in terms of magnitude completeness, and these are magnitudes estimated from the traditional geophones, it looks like DAS was complete down to -1.4, and the geophone was complete down to -1.7. So you're losing a little bit for DAS, but you get all the operational benefits. And yeah, do the value calculation, they get same results. But the important thing, I think, is how much you lose in this case by using DAS. You can also do some basic location work. As I mentioned, we have this complete azimuthal symmetry for DAS, so we can only resolve depth and distance from the well, and not absolute location. So it's not really a fair comparison, but if you collapse the geophones to this 2D plane and take their locations, we get that the locations are practically the same. And we were also able to estimate magnitude from DAS. This is like some sort of semi-empirical formulation that is based on strain directly. And we get a pretty good correlation between the magnitude estimated with geophone and the one estimated with DAS. So it's not a one-to-one, but it's pretty close. So we can also get at least reasonable magnitude estimations from DAS. So that was it about the vertical part. Now let's go into the horizontal, and more specifically into some unconventional reservoirs. So the acquisition setup, this is a collaboration with Chevron. We've got 3 wells. The one in the middle is equipped with fiber along its entire length. But we have these 3 wells, and I only plotted the horizontal sections here. They're all in the same reservoir, hit the formation, and they're all parallel. So we've got 3 wells in the reservoir at the same depth, which is something pretty cool. And they are all perforated and stimulated. And everything is recorded by the fiber. So there's a very rich data set. In terms of kind of like the geological settings, we've got a vertical well drilled a few hundred meters away from those. And we've got seismic velocity, density, and gamma ray. This is actually inverse gamma ray. But so you can see that the reservoir marked here in between dashed black lines shows up as an area of low velocity, low density, and high shale content, right? Because this is inverse gamma ray. We also know that this reservoir is very anisotropic. And we know this because we've got sonic logging in the horizontal well, in the DAS-equipped well. And these are P wave, SH wave, and SV wave velocities. So we can see a very obvious shear wave splitting, indicating the anisotropy. So this reservoir is pretty complicated. I mean, it's anisotropic. We have this like intrusion here in the middle that we're not 100% sure what it is. But generally speaking, it's an area of low velocity and low density compared to its surroundings. But let's forget about all that and think about the simplest waveguide that I could think of. This is a modeling exercise, and this is a 2D isotropic elastic world. It's only made up of 3 layers. I didn't even bother changing the density. It's just 3 layers with different velocities, with the layer in the middle having the lowest one of all. And I'm going to generate a source in that low velocity layer, which would be what happens if you have a perforation shot or a fracture opening. And we're going to look at the seismic wave field. In this case, it's going to be the seismic wave field along the X direction, so closer to what the DAS would measure. As we remember, it measures stream. And of course, I'm going to color code the seismic wave field. Blue and orange is going to be above the reservoir, yellow and black inside the reservoir, and green and pink below the reservoir. So let me start that source. There's a lot going on, but what's important to focus on, I think, is this event here and this event here. Because these die off pretty quickly, but these 2 events seem to be confined to the low velocity reservoir and to propagate for some distance without losing too much energy. This one seems to be actually going on for even longer. And it turns out that these are actually 2 types of guided waves. Movie is going to start again. And you can see, of course, a big bang of seismic energy. Everything's a big mix. But then you get these 2 modes starting to separate, one's faster than the other. You can see that they are very clearly dispersive, right? You can see the low frequencies are propagating faster than the high frequencies. This one seems to having this triangular pattern, and this one doesn't. So let's try to stop time for a second. This is whatever, 0.3 seconds after the source was initiated. The one on the left, the slower one, is actually more of a classical and normal mode. Again, classical guided wave. You can see it is dispersive, right? Low frequencies and high frequencies. It's closer to shear wave propagation velocity. And outside of the reservoir, we get this exponential decay as a function of the wavelength. So basically, low frequencies kind of penetrate into the surrounding formations, whereas high frequencies, not so much. The other type, the faster one, closer to P wave velocity, is actually a leaky mode. This is something that's a little bit less intuitive, but you can think about it as some constructive interference of P waves that also radiates energy in the form of S waves. And these are these like triangles that reminded me of Mach waves when I first saw this movie, but are actually some S wave radiation. So we've got these 2 different guided wave modes that propagate in this very, very simple structure that's just like a 3-layer model. I think it's something, to me, it was a bit humbling, like how such a simple model can create such a complex propagation. And luckily, because we have the fiber in the reservoir, we can actually observe these guided waves. So this is a perforation shot. So again, a controlled explosion of the well equipped with fiber. So this is actually like, you can think about it as like propagation along the line, and you can see this very nice dispersion, low frequency, high frequencies. We have this branch here, which is probably like a higher mode of the guided waves. As you know, guided waves, like surface waves and love waves, have multiple modes. We see primarily 1 mode, and that's the leaky mode. We know this just from the velocity. And almost no normal mode energy. When you go to the cross well, so now you've got one of the red wells, one of the offset wells being perforated. There's about 250 meters to the DAS well, so the move outs now are going to be closer to hyperbolic, but you can still see this dispersion, right, with low frequencies and high frequencies. But now you see a second mode, and that's the normal SH mode. So it's basically we see both the leaky and the normal mode in the field data, which is I think pretty cool. Yeah, let's keep that. I'm running out of time. So to kind of summarize the properties of all these guided waves, I basically stacked multiple perforation shots, both in the DAS-equipped well and in the offset wells, to kind of try to increase signal-to-noise ratio and increase the visibility. This is an interesting shot from the DAS-equipped fiber. For about 20% of the shots, it looks like we also have this slower mode. It is actually normal PSV mode. I didn't have time to go into the math, but when you go into a 3D world, the normal mode, the slower one, actually splits. You've got one that's SH and one that is PSV. And because of the anisotropy, they have very different propagation velocities. Again, apologies for not going into that, but that requires some pretty awful math. And as I mentioned, sometimes at the frac plug, we see some conversion to this mode. It's not for all of the shots, but we get there sometimes. For the cross well, we see mostly the normal SH mode and as always, the leaky mode. One way that we like to look at this data is in the frequency phase velocity domain. If you've looked at dispersion curves of surface waves, for example, that's something that you're probably quite familiar with. So for the same well, as I mentioned, we see mostly the leaky P waves with this like higher mode probably, and a weak PSV phase that we could see sometimes. Cross well, we see the leaky wave exactly in the same location in the spectrum and the normal SH. And if I just take the sum of these two images, which means nothing from a physical point of view, but it's nice to visualize, we can see like the full behavior of guided waves. So they have interesting properties. They are dispersive. What I want to point out is this point right here. We are getting to 700 hertz. And if you look at the velocity, we're talking about wavelengths of like 5.5 meters. So we're talking about stuff that is extremely short, that I think without fiber could not be recorded, simply because you would need to deploy a geophone every meter, which is probably impossible to do. And that's where the spatial resolution of DAS really kicks in. So we use these guided waves to look at the horizontal growth of fractures. Again, maybe not the best drawing on the planet, but let's say this is a map view. We've got two wells. Let's say well number 1 has a fiber and well number 2 is being perforated and stimulated. So those are fractures. Let's look at the next perf shot, the next explosion. This one's going to generate guided waves, right? We've seen. But the interesting thing is some of these guided waves will go through unstimulated part of the reservoir, so basically undisturbed rock, whereas the other one to the right are going to cross open fractures. So let's see if maybe there's a difference in the data that we get on both sides of the source. So this is what we saw before. This is the undisturbed part of the reservoir. We see these two guided wave modes, the leaky one and the SH normal mode. When we look on the other side, going through the area, we can see something very interesting. For the P waves, I mean, the leaky waves, there's not a huge difference, at least not to the naked eye. But when you look at the SH waves, the normal SH waves, you can see a huge imprint of the fracture, right? I mean, I guess that makes some sense because if you're looking at S waves, the velocity inside the fracture should be 0 theoretically, right? I mean, it's fluid or gas. So we expect a much higher imprint on the shear waves compared to the P waves, but that's a pretty obvious signature of going through the fractured areas. And just to show you that this was not some just lucky shot, I took 6 different perforation shots from different parts of the wells, and I'm always showing 1 kilometer of fiber right in front of the shot. That's why sometimes here you will see noise. That's basically just the end of the fiber. And left side is undisturbed rock, right side is previously stimulated. And when I remove these ugly curtains, you will see that there always seems to be some asymmetry between the left and the right side for DSH normal modes. Now, I will say right away, the behavior here is extremely complex, at least in my eyes, and it's not always the same imprint that the fractures have on the wave. So for example, this is the one we saw before. The wavefield here looks completely shattered, right? Here, it looks more like some sort of a slowdown. Here you get some scattering. Here you get some shadow zones. It's hard to exactly quantify what's happening, but there always seems to be some difference between the unstimulated and previously stimulated parts in terms of their interaction with the guided wave. So because it's so complicated, we try to do something very kind of like first order analysis. And we simply looked at sets of 5 perforations. The way these things go in the field is you've got like 5 explosions going off within 2 or 3 minutes. And then you need to wait hours for the next stage. And within hours, the earth can change, fractures can close or something, the stress regime can kind of reorganize itself. But when you're looking within a 2 or 3 minute frame, hopefully the earth is the same. And we found out that if you look at the different shots, so basically with shots moving away from the previously stimulated area, right? Because they start at the end of the well and they work their way backwards, we find that the distance, basically the horizontal distance at which we start seeing this change in the guided wave increases as the shot moves away. So for example, for the shot the closest to the previously stimulated area, we can manually estimate the kind of like the threshold distance at like 50 meters. And here it's at about 120 meters. Again, this is all like very, very soft and very qualitative, but we explain it with this very, very naive maybe model, saying that we've got an area that's previously stimulated. This is again in the map view, and this area has some horizontal growth that's known as the half length. Now let's look at this shot, the shot closest to the previously stimulated area. It's going to generate guided waves. Let's assume they propagate in straight lines, and at some point they're going to start crossing that area, and then something's going to happen to these guided waves. They're going to change a little bit. So for that shot, this ray here is the first that's going to encounter the previously stimulated area, right? So from that point and to the right, we will see some disturbance. Now, if you go to this shot, now this is the critical ray. So you can see that as the shots move away, actually the horizontal distance between the source, the shot location, and the fiber channel at which we kind of detect that change increases. And this is like high school geometry. You can do some linear regression, and from that estimate the horizontal growth of the fractures. So we did that, and we did that for different stages. This is the value that matters. We found the horizontal growth is around 165 meters, something like that. It makes sense in terms of the well spacing. But interestingly enough, there is also some quite large variation between the different stimulation stages. So that means that not all fractures grow equally, which I think is interesting to look at. Now, another way you can look at the fractures is directly, right? When a fracture opens, it releases microseismic energy. And this is, I think it's a beautiful event, one of the strongest we have. This is a microseismic event, and it is so strong that not only we can record it entirely, along the entire horizontal portion of the fiber, but we can actually see it all the way up to the surface. So we said the well is deviated, but at some point it has to climb back up. So you can see that this microseismic event generates 3 types of guided waves. We have the leaky waves here, the guided SH here, and in this case, very strong guided SV. You see this very nice like dispersion behavior. And whenever the fiber exits the formation, which is at about this blue location, we can see that all this dispersive behavior disappears, and we just go back to body wave propagation. So this is the P wave, and this is the S wave. And this anisotropy, or this splitting, actually, again, disappears when both converge back to this kind of body S wave that gets all the way to the surface. And that's really nice. You can see that when fiber gets out of the formation, we do not see these events anymore. So that strengthens the theory that these are guided waves. And from a practical perspective, again, of event detection, in about 30 minutes of data, randomly chosen, in a surface-based microseismic analysis done by a contractor, there were about 200 events. And I just manually went through half an hour of that data, and I could see more than 10 times as many events, or even 12 times as many, without any specific processing, just like visually looking at it. And that makes sense, right? I mean, we are very close to the events. If you are at the surface, the events have to propagate like 2 kilometers up before you can see them. Whereas with dust, you can be 100 meters away from them. So you have much more chance of seeing something. So the problem with dust, as I mentioned, is the directionality, right? So we talked about the fact that you basically have symmetry around the fiber in terms of location. You also have the problem that individual DAS channels are noisier compared to downhole geophones, but that's more of a technicality. The big problem is the symmetry. So in the general case, we have circular symmetry, right? If we have a constant velocity world, we can get the location along the fiber very precisely, and we can get the radius of the event from the fiber, but we cannot get the right location, not in the absolute sense. And the only way you can solve this, seemingly, is to use more complex DAS acquisitions. You can use the deviated part of the well, but the problem is that the signals might be too weak in that section. Or if you're lucky, you can have multiple DAS wells, and that's great, but that's costly. I mean, having multiple DAS monitoring wells is not something you see in every operation. Or you can use guided waves. And it turns out that guided waves have some pretty interesting properties that can help us in saying something about the location of the event. So in a joint study with Owen Huff from the Colorado School of Mines, we saw that guided waves dominate or are present in the seismic records only if the event is generated inside the low velocity reservoir. So this is just, again, a modeling exercise in 3D, but when the event is inside the reservoir, you can see it generates these clearly dispersive events. When it's outside the reservoir, we mostly see body waves. And if we look again at the dispersion domain, we can see this like low velocity dispersive event that is simply inexistent when the event is outside the reservoir. So that means when we see this dispersive behavior in the data, we know the event has to originate inside the reservoir. And that's useful because if we know that the guided waves indicate that the event originates in the reservoir, we also know that their propagation is confined to the reservoir, right? Because we saw in that movie that the reservoir is actually kind of leading the seismic energy and not letting it get out, right? As a result, by the way, the loss is weaker than for body waves, so they can propagate for longer distances. But visually, we said we have a fiber and we have the circular symmetry. Now, if we see guided waves, we know the event has to be coming from the reservoir. So we can actually intersect that circle with the reservoir. And in our case, the reservoir is pretty thin. So we are actually reduced to a 2D problem, right? I mean, if we assume that the depth of the reservoir is negligible, we actually can resolve the location. So not completely, because we still have left and right asymmetry, but because of the way these stimulation programs work, they're not stimulating both sides at the same time. They are either stimulating from the right side of the well or from the left side of the well. And therefore, it's very easy to just attribute all the events you see to whichever side is being stimulated. So with guided waves, we actually have a shot at locating events. Now, in order to do that, we first need to detect these events. And we did this with machine learning. Fantine Huot did a great job at that. And I will not say that I understand what she did. What I did was, with the help of another student, we manually picked something like 7,000 events as training for the machine learning. So machine learning is great, but there's always someone doing, I'd say, I don't know, the less glorious work behind it. So we trained the network and we applied it to 10 stimulation stages, about 2 hours of data each, and we found more than 100,000 microseismic events. And now we want to locate these events. And we talked about the guided waves and how they have unique dispersion properties, and we're going to make use of that. So the idea is that using the perforation shots that we discussed, they have very high frequency content. We know their location. So we can measure, if you want, the ground truth properties of the dispersion nature of the guided waves. So we know exactly how these guided waves should behave. And the way we did it, we take the perforation shot. Instead of having this hyperbolic move out, it to distance between source and receiver. Here it's like distance along the fiber. Here it's source receiver distance. So now things should be more linear. And we convert this image to the frequency and phase velocity. And now we know, okay, guided waves should have, for this mode, dispersion in this area. I mean, that's where the dispersive energy should be. And we want to locate events by saying, well, we know that if we see an event that has the dispersion energy in that specific portion of the image, we know we got the right location. So basically, the source location is hidden in the way we generate these images, right? I said that the first step was distance along the fiber to source receiver distance. Now, if you know where your source is, like for a perf shot, that step is trivial. But if you do not know where your source is, this is actually what's going to control your location. So basically, we're going to generate many possible dispersion images for different source locations. Through that mapping, we'll see differences in the dispersion, and we know where the energy should be because we measured it from perf shots. So this is, again, a very simple modeling exercise. We assume we know the location along the fiber exactly because that's the easiest part to do because you have great resolution. And this is the dispersion images. Let's just look at those for sources at different distances from the array. So that's of course the right distance. You can see that things are roughly linear here. And if you look at the frequency and phase velocity of dispersion domain, you can see that the energy is focused right where it should be. Whereas if the location of the source is wrong, you can see that the energy is more smeared, and also it's not at the right portion of the spectrum. Then you can define some objective function and use that to locate the events. We just use the energy inside this zone we define divided by the energy outside, just so we correct for event magnitude and don't let us affect. Don't let it affect us. Yeah, let's skip that part. Just a way to automatically estimate the location along the fiber. We're basically looking for a point around which the slopes of the events are reversed. We're basically looking for an image, kind of a mirror image. We did it using a nice technique from John Claerbaugh's book, basically estimating the dip of the image. This is, by the way, what most microseismic events look like. So not terrific quality. So as I mentioned, we had more than 100,000 events. Only a relatively small portion were good enough to be reliably localized, which means we could automatically pick their apex with high certainty, and that this dispersion energy focusing worked well. So we threw away many weak events and possibly many events that did not have guided waves, which is good because we cannot locate them anyway because they're not within our set of assumptions that the guided waves are dominant. And as I mentioned, we still have the left-right ambiguity, so we just attribute all events to the stimulation, to the stimulated well. And when we did the full location for 10 stages, we got this image, which we really liked. So each stage is color-coded. We've got 5 on each well. And this image tells us, I think, quite a few things in terms of interpretation. So first, it seems like all the fractures have some consistent propagation direction, right? Which is not perpendicular to the well, which is interesting. I think this might be indicative of some regional stress in the reservoir. In terms of the absolute growth, so basically how much these fracture sets grow towards the fiber well, it looks like the absolute number, which is around 160 meters, is validated by the previous study that we did with the perf shots. And you can also see, I think, a fundamental difference in the way the fractures behave, in that in the north part, the fracture goes kind of both towards the DAS fiber in the middle and away from it. Whereas in the south, well, it seems to be predominantly towards the DAS fiber. So clearly there is a difference in the geology here that makes this different fracture behavior. Now, I have to say, I don't know anything about that reservoir. I don't even know where it is for IP reasons. So I cannot say much about the reservoir, but at least to me, it looks like there is some interpretation potential from these guided wave-based locations. So yeah, I'm slightly running out of time, so let's skip those and jump to the conclusions. I hope I convinced you that, and that's going back to the first part of the talk, the vertical arrays, that DAS is an efficient tool for long-term seismic monitoring. It outperformed a local standard kind of surface seismometer array. It was slightly worse than downhole geophones, but I think it's much easier from a practical perspective. For example, not having to lower geophones every time you want to do an experiment. Of course, if you want the full location and the full focal mechanism, you're going to need more complicated acquisition geometries, not just a single vertical array. But you can think about fibers on the surface or multiple wells or deviated wells or things like that. In terms of the, let's say, the unconventional or the reservoir characterization potential, I think that DAS in general is great, and guided waves specifically kind of take the full advantage of DAS or vice versa, simply because DAS can record things at very, very short wavelengths unaliased. There's a huge potential for structural inversion using these guided waves. I did not talk about it, but there are a few studies, among others, Bin Luo showed some basically 1D inversion, including anisotropy, to reconstruct the properties of the reservoir simply based on the exact behavior of the dispersion curves of the guided waves. There are some people working on full waveform inversion of these perforation shots. But what I showed, I guess, is maybe more kind of like first steps in that domain. But we could use them for estimating the horizontal fracture growth based on perforation shots and how the guided waves they generate interact with the fractures, and also directly from microseismic analysis with this like nice hack of saying, well, if we've got guided waves, the event is in the reservoir is pretty thin, so location becomes a 2D problem, and we can actually resolve something and get an image that can be interpreted. So yeah, thanks to Chevron for the second part, for the data and the permission to publish. The first part is an open data. If you're interested into going into DAS, I think it's a nice project. It's the Forge project led by the DOE, and then lots of people who paid for things. And yeah, I think we can go for questions. And going back to that special event, if you have a guess on at least what I think this is, feel free to guess. That's it.
Oh, thank you, Ariel. That was some spectacular data. So we can take questions in the chat, or use the raise hand, the virtual raise hand functionality.
Yeah, Damien, go ahead.
Hey, Ariel, terrific talk.
Hey.
Thanks so much for joining us through a fiber optic cable from across the Atlantic. So I actually have a question. It's more about the instrumentation and technique, I guess. But what I've seen from DAS is that it's really good for small strains. And so you mentioned early on in the talk this idea of it being quasi-linear in the response to strain. So for things like this high frequency stuff and earthquake detection, I guess I'm wondering, as a geodetic tool, or if you wanted to put this on ice, let's say, are there limitations in terms of the high strain end?
Yeah, actually, it's a very good point, and I had to make some assumptions during this talk. I didn't want to get into the details. The problem is that because it looks at phase change of light, basically, if you have too much strain, you're going to go for 2 pi, and you're basically going to lose phase. And therefore, you're absolutely right. And every interrogator has a limit. And depending on its specific setup, you can sometimes change that limit. But yeah, if you're going to see a huge event in terms of strain with a standard acquisition like this, you're going to lose the phase. I can tell you, for example, we've been doing examples very near surface, and we use hammer shots, right? And when you hit the hammer directly on the fiber, you lose coherency of the data, simply because there is too much strain induced on the fiber, and then the phase starts looping. You're basically losing the phase. So it's absolutely right. And this is a limitation, and it really helps knowing which strains you expect before setting up your optical parameters and so forth. But yeah, very, very good point.
Thomas.
I saw people raising their hand, but I'm having a hard time. Oh yeah, okay, got it. Thomas, go ahead, yeah.
Can you hear me?
Yeah.
Okay, back at the beginning, you talked about ray forming. I was just wondering if you experimented with the number of elements in the array and the delay you gave to each element. You could actually do some beam forming and try to find out where the energy is coming from.
Yeah, I mean, I think eventually what I did, I mean, it's eventually beamforming because I'm trying different angles of incidence and just trying to see if the energy is coherent. I think it ends up being the same way. Honestly, I did not experiment with like downsampling the array. I just used the full resolution because computationally it was not the end of the world. But also, yeah, I did not use the beamforming formulation directly. I just think it ends up being the same principle of like a plane wave hitting your array. Just in my case, I think the difference was that the velocity within the boundaries of the array changes. So you cannot use the same angle if you want for all the channels at the same time. So that's why I went through this maybe like slightly convoluted application, but basically it's been forming, at least in terms of the initial assumptions.
So if the length of the downhole cable is greater than the depth of the source, you might be able to get some sort of triangulation on its position.
Yeah. Exactly. Yeah. I mean, in this case, you're absolutely right. In this case, the event was always below us, so it was relatively easy. If the event could be within the array, then let's think about the boundary. So if it's right on the array, you would see some triangle in terms of the arrival times, right? And if it's far away, you'll start seeing some hyperbolas. And then you could actually locate this based on the curvature, right? But in this case, because we knew the events were down, this type of like single angle scan was so much faster that I like this reduction in complexity. But in theory, you're absolutely right. I mean, you do a full location based on the curvature.
Well, you could do the curvature and the amplitude, because if you got the angle of each pseudo-formed array and the number of elements in it to reach a maximum, then you could say that's the direction the ray is coming from.
Yeah, exactly. Yeah, exactly. Yeah.
Okay, thanks.
Yeah.
Looks like we have a question from Doug.
I got to unmute. So, Ariel, thank you for the very interesting talk, first of all. Boy, it looked like there was significant shear wave splitting in some of those slides. Maybe it's just scale. But what do you think? Do you think in some way if you...
Oh, no.
Go ahead.
No, I'm going to go there. But yeah, I think it was like 30% difference. So very noticeable shear wave splitting. So I don't remember the number of the slide, but we'll get there.
I guess the question I have is, if you relate seismic anisotropy to local stress conditions, how accurate, or what can you say about the local stress conditions right along the wells before and after fracking?
Yeah, I mean, the problem with the waves that I'm looking at, which is mostly the crosswell stuff, the problem is, we're seeing an average of the properties along the entire propagation path. So like being able to separate exactly the conditions near the wellbore, we might have to look at kind of the same well experiment where we had the DAS fiber perforated. But then the problem is that you're competing with tube waves, and it's tricky. I mean, one of the PhD students at Stanford is looking into full waveform inversion of that, and hopefully try to recover, let's say, the elastic properties, anisotropic, and hopefully we'll see a difference between the previously stimulated area and the unstimulated part. But I don't think that's going to work from the cross well. I think you have to work on the same well data. The cross well, you're going to see more like an average property of the medium, not of the wellbore conditions. But that's something that we thought about it, and we still didn't have the capacity and the time to do it. But I hope we'll get there.
Because it might say a lot about how you would go back and recomplete a well and refract different intervals.
Yeah. Absolutely. Also, in terms of like hazards and stuff like that, it could be super important. And the resolution, the frequency, the frequency is there. I think. I mean, if you're looking at wavelengths of 5 meters, I mean, you might have a shot at high resolution, really high resolution. Hopefully, full waveform inversion will do something good for us. I'll keep you updated.
Yeah, great. Thanks again. Very interesting.
Sure. Cool. Thanks.
Any last questions out there?
Final guesses on the special event? Oops. So I can say my theory about this one if we don't have any more questions.
Go ahead.
Go ahead. Okay, so I'm thinking that this is, oh wait, Doug wants to guess.
Well,
oh no, okay.
It looks like it's propagating at p-wave velocity. If I'm looking at the right event.
So my guess, my guess is that this is actually a refraction event from a very shallow source, because you can see that below this 800 meters, we basically don't see a signal. Whereas for events that were coming from far below, it was more continuous. So I'm thinking that this is a very shallow event that goes down to the granite, kind of serves the granite contact, and then gets to the fiber. And that's why we don't see stuff below the granite. But that's just me. I don't know if it's true or not.
Okay.
Just like I just felt it was a cool event that was kind of unconventional. So anyway, that.
Okay, yeah, because you see a lot of things that are hard to explain, don't you?
Oh yes, absolutely. Yeah, and also you have to take into account the directivity of DAS that can mess some things up. Yeah, this is an interesting conversion here. This might be a P to S conversion right there. There's you can see all these code. I mean, I'm calling them coda for lack of better words, but you see coherent energy coming in later. Yeah, that's what's so nice about DAS. You can do much more than just, oh yeah, PNS. Okay.
Yeah.
I mean, you can really start saying something about the source and the medium. Yeah.
I was looking at the wrong event, so okay, very good.
You're not. Yeah. I had more time to think about it than you, so it's a bit of an unfair. Yeah.
Oh, thanks again, Ariel. Please, everyone, convey your virtual applause. And there's still a couple of slots left over lunchtime, Texas time, to meet with Ariel if you want to follow up on these conversations. But yeah, very, very interesting stuff. Thanks.
Cool. Thanks for the invitation and the introduction and so forth.